Good evening. So today I thought I'd talk about something that's very dear to me, which is called an op amp, or what op amp stands for is operational amplifier. If you can't read my handwriting, click off the video. It's not going to get any better. But essentially, what that means is it's an amplifier that can perform operations. So it can add signals, it can subtract signals, it can even multiply and divide them if if you use a bit more complicated circuitry, but it can even integrate, differentiate, and even perform complex functions, right? So this is what the symbol for an op amp looks like. It's this little triangle. It has a negative and a plus side, and so it has a negative input, a positive input, an output, and power inputs. So a few of the properties of an op amp is that it has an infinite input impedance, that the current going into each terminal is approximately zero, and that the voltage difference between these two input terminals is zero, or approximately zero in the real world. It has a theoretical infinite gain, a theoretical infinite bandwidth, and a theoretical zero output impedance. You probably noticed I said theoretical a lot, but that's just because most of this isn't true in the real world. We just kind of take it as true when we're doing analysis. And this is the equivalent circuit if you want to look at that. Basically, you just have a really large input resistance and a really small output resistance. And yeah, this is negative, this is a positive input. All right, so let's begin with one of the more simple versions of the circuit down here. This is called an inverting amplifier because, well, we'll see why in a second. So let's do some analysis on the circuit. So as you can see, we have two resistors and one op amp in the center here, with the non-inverting input, the plus, connected to ground, and the inverting input connected between the two resistors. So to analyze the circuit, the first thing we should do is label our nodes. So the first node here is going to be our input, so we're going to call it Vin. This node here, we don't know what it is, but we're just going to call it VA. And this node here is the output, so we're going to call it Vout. So if you know nodal, or if you've ever studied circuit analysis, you should know something known as nodal. Basically, all this means is that the amount of current going in has to be equal to the amount of current out in one of these little nodes, which is represented by a dot. So the amount of current flowing through R1, we're going to call it IR1, has to be equal to the amount of current flowing out of this little node. We know that there's no current going through the inverting input, because this is how it's kind of defined up here. There can't be any input current because there's an infinite input impedance. So that means that the amount of current flowing out is just going to be IR2, which we're going to label here. So what this means is that IR1 is going to be equal to IR2. So IR1 is equal to IR2. Okay, so how can we calculate each one of these? Well, the voltage across, if we remember Ohm's law, voltage equals current times resistance. So the voltage across R1 is Vin minus VA. So Vn minus VA, we're going to divide that by R1. Okay, now the current flowing through R2, IR2, is VA minus Vout. So this is going to be equal to VA minus Vout. Okay, over R2. I should mention that you have to divide by R2 to get the current. Okay, so this is pretty good. Now we don't know what VA is. However, one of the properties of the op amp is that the voltage difference between these two terminals is always zero. So we could say that VA is just equal to 0 volts. So it seems like it's a ground. It looks like a ground to the circuit. So we could cancel these out, these two VAs, as they both go to 0. So we get that Vn over R1 is equal to the negative of Vout over R2. So to solve for the output voltage, because we want to know what the output to the input is, we can multiply both sides by negative R2. So multiply both sides by negative R2, right? And then what we get is that voltage out, you guys can see that okay, right? Yeah, I hope so. Voltage out is equal to negative R2 over R1 multiplied by voltage in. And what this means is that the voltage gain, which is the output over the input, so dividing both sides by the voltage in, AV is then equal to negative R2 over R1. So that means that the voltage gain depends on these two resistances. So let's do a real world example using, let's say we want to have a gain of about negative 10. So we're going to select R2 to be about 10 kiloohms, and R1 is going to be equal to 1 kiloohm. So we're going to do this. I'm going to show you how you can actually make this circuit, and hopefully it will work for us.
Alright, so this is the circuit. I just put it in LTSpice just to kind of, before we go into the lab. And as you can see, when we have the input here, it has an amplitude of around 100 millivolts. And something to keep note is where its peaks are. It goes up and then down, right? And this is the output, right? The output is at around 1 volt, and that's exactly 10 times whatever the input was, right? Which was 100 millivolts. 10 times 100 millivolts is 1 volt, right? And something else you'll notice is that when the input is high, the output is low, and when the input is low, the output is high. This is why it's called an inverting amplifier. It not only amplifies the input signal, but it also inverts it. And one other thing is when you power the circuit, it is recommended to use a dual power supply. At least in all the circuits that I've ever found for op-amps, they all use dual power supplies. If there's any exceptions to this, please let me know in case it's wrong. But if you don't have a dual power supply, what you can do is you can build a circuit like this, where you just basically create a voltage divider with some capacitors for keeping the voltage stable, and you just take the center voltage of this as your common, right? Because all the common is it's just a reference point. If this was a ground, it would be different, but just because it's a common, it's a reference point, it's completely arbitrary where we put it, right? So we're just putting it here in this circuit just to make our lives a little easier, and that's pretty much it for this part of the video. So let's get to the lab.
Alright, so here's the actual circuit. It's a little bit hidden up, but as you can see, we're using a TL074 quad operational amplifier. There's the 1 kiloohm resistor, 10 kiloohm resistor, and these are the two circuits creating the voltage, the resistor, capacitor, and capacitor creating the voltage divider. So that's what we have. As you can see, this creates an output signal that is 10 times larger than the input, and if we amplify the input a little, you can also see that they are exactly out of phase. So there we go, that means that this worked. Okay, so that was how the inverting amplifier works. So now let's work on a non-inverting amplifier. So this is what the circuit would look like for a non-inverting amplifier. We have the input voltage attached to the non-inverting input, and then we have a resistor connected to the inverting input to ground, and a resistor connected to the output from the inverting input. So let's analyze this circuit. I'm not going to be doing a practical demonstration of this circuit, but I will be analyzing it. So first thing to note is that there's no voltage difference between each terminal, which means that Vin has to be equal to VA. So Vin is equal to VA. We're going to use nodal again, so we're going to say that the sum of current, sum of I, entering node A is going to be equal to 0. So the current going this way, plus the current going this way, plus the current going that way, all of these currents add to 0. We know the current here is 0. The current going into the inverting input is 0. And we could calculate the current going through each resistor using Ohm's law again. So the current going through resistor 1 is VA minus 0 volts divided by R1, or VA, or VN, because VA equals VN, divided by R1, plus VA minus Vout divided by R2, or VN. I shouldn't say VA because, yeah. So, based on this, we can actually find what Vout is. Oh, and this has to be equal to 0. So what we could do is we could add Vout to both sides, and we get that Vn over R1 plus Vn over R2 has to be equal to Vout over R2, because we add it to both sides. And what we can do to cancel out, to get Vout on its own, we can multiply both sides by R2. So I'm going to times this by R2, and we're going to take this whole thing, multiply that by R2. So as you can see, these R2s cancel, and multiplying this through, we get that Vout is equal to, we could factor out the Vn here, and this would reduce down to Vn multiplied by 1 plus R2 divided by R1. So as you can see in this formula here, because there's no negative sign, this means that it would be in phase, which means that the peaks of the input would line up with the peaks of the output, which I'll show in a simulation pretty quick. Yeah, that's pretty much it.
Alright, so this is the non-inverting amplifier shown in LT-Spice. So as you can see right here, we have the input voltage connected to the non-inverting inputs, and you know, like the previous circuit. If we use the equation, R2 divided by R1 plus 1 would be the gain, so that's 10 divided by 1, which is 10, plus 1, which is 11. So the output is the input times 11, and as you can see, 100 millivolts times 11 is 1.1 volts, which we see in this graph. If I just zoom in, yeah, 1.1 volts. So yeah, that's basically how you would do something like this. And as you can see, the peaks and the troughs line up with each other. And that's what the non-inverting amplifier looks like.
All right. So, now that's all cool and all, but, you know, what could we actually use this for? This is an example of what we could apply this chip for. So this is a microphone amplifier. Basically, we take a weak input signal from the microphone here, and it goes through this amplifier circuit. This circuit here, if we kind of just cover this up, as you can see, is very similar to the one up here. The only difference is that we have these 2 resistors and 2 capacitors, and all these are really doing is providing a bias to the circuit, because amplifiers need to be biased so that you get a positive amplification and a negative amplification for positive and negative signals, right? So, this circuit's just using a TLO74 quad operational amplifier. Good chip, highly recommend. I love it. I love the TLO74 quad operational amplifier. It's using 12 volts, but you could probably do this with 5 volts or 9 volts if you just got like a battery. And it has a gain of around 1,000, which is about 60 decibels. Actually, it is 60 decibels. So, yeah, this is what I'll show you. Really recommend the TLO74. Really good chip. So this is an actual application circuit of that of an amplifier using an op-amp. As you can see, we have a probe connected here. It's connected to the negative, and it's just connected to the output of the amplifier, and we have a microphone. So when I speak, as you can see, the that's what my voice looks like. It's picking up my voice and it's plotting it on the oscilloscope. It's a little bit noisy, but it does work, and it's pretty cool. There we go. That's how it's done.